Cool. Well, hello, everyone. My name is Jake. Some of you may know me as Ferris. I really, really love Super Nintendo. If you didn't know that about me yet, you really, really will by the end of this talk. You might have seen me in some demo scene groups, such as Youth Uprising. I've also been an active member of the group Outtracks. Most recently, I've been an active member of the group Elix, which is a Super Nintendo-only group that I formed April of last year. We've done 2 demos so far, released at 2 parties. We won first place with both of them, and we're hoping to keep that streak with the next couple. So I am obsessed with process. And one of the things is that just getting something to work just is not enough for me. I need to learn something new during every project. I need to optimize and minimize some kind of the workflow. I'm really, really obsessed with silly things like that. It's not enough to get to the goal. I have to do it awesome. So I really love to do that, even if it's unorthodox. And actually, that's especially if it's unorthodox. If I can do something strange and still get it to work, I just love that stuff. So even if that means there's loads of work elsewhere, this is totally what I try to do because it's super, super interesting work. So this talk is going to be about sort of my journey into SNES development and making demos for the platform, how I've arrived at sort of my current tool chain and all that kind of stuff. So let's dig in. So first things first, I'm guessing most of you have seen what a SNES looks like before. But if I asked you what it looks like, you might say a couple different things. You might say it looks like this. Some of you might also say it looks like this if you grew up anywhere outside of the US. Some more geeky members of the audience might say it looks like this. That's the one that I read first, so that's fun. But for our purposes, this is sort of the model that we're gonna work with. So there really aren't that many sort of individual units. You'll see I've split them up. And of course, this is really overly simplified, but it's all we need. So the main system has the CPU, and it has 128K of RAM. It also has some other peripherals, like things to interact with the controller. Has some expansion port stuff, but nothing that really concerns us when we're making a non-interactive audio-visual presentation. As such, beneath that, you can see I've put the cartridge. That is pretty much a 1 to 4 megabyte ROM. You never really went higher than that in the actual games. I think a couple went to like 6 because it was expensive then. On the left there, you can see I have the audio. What's interesting about the SNES is the audio unit is its own self-contained unit with its own CPU and RAM and its own DSP and everything. And that's pretty interesting, but we'll get to that later. On the right there, we have the video unit. Video unit is made up of the PPU, or pixel processing unit. It basically takes tile data that's stored in 64 kilobytes of RAM and just displays it on the screen. It reads colors from this thing called the CG RAM, which has the worst name ever, because it's a character generation RAM, but all it does is specify colors. And then it also has this 544 bytes of OAM, which is object attribute memory. This describes attributes of the sprites. You'll see Mario jumping around on the screen, and yeah, those say where Mario's going to be, what he's going to look like, and how big he is. We won't get too much into those details in the talk because, be really interesting things later. Now, the one thing that's really, really awesome about SNES, the CPU is actually really terrible. It's this weird sort of 2.5 megahertz thing that can be bumped up to 3.5 if you use a weird memory map, and it switches between 8 and 16-bit modes, and it's just god-awful. But the nice thing is that you almost never have to do anything with it because you have DMA and all this other nice hardware around it. So as long as you can optimize your workflow to actually use the hardware well and use this DMA, then you're pretty golden. So if you guys have never seen sort of any old school coding before, this is going to be a super duper short crash course on kind of how this usually works in the general sense. So when you write code, you might write code that looks like this. This is the classic Hello World example written in C. You can see it's not too bad looking, pretty short, pretty cute. You've probably also written code like this. This is C# for some OpenGL kind of thing. When you're doing old school coding, though, you usually don't get to work with these kind of high-level languages. You don't even get to work with C. You usually have to work with assembler. And assembler looks like this. This is actual audio code from my music driver in these SNES demos. The thing is that there's a lot of little tiny bits. When you actually look at this, you can kind of tell that it has sort of the structure a C program would have. You can kind of see where like different subroutines are and different kind of branches and loops. And because of that, it's kind of not that difficult to write this code. What is difficult, I guess it's more tedious, is that there's so many things can go wrong.
because, like, yeah, your compiler's not helping you at all with any of these. You just do whatever. You're speaking the language of the system to the system. So it's, yeah, it can take a lot of code. So I'm not really a big fan of doing a lot of assembler hacking because it really just kind of feels like a bummer. You're wasting your life away twiddling bits. That's kind of not very fun. I mean, some people like it, and that's cool, but I always want to try to do something more. So I want to sort of talk about how I got into this mindset and sort of how I went from some guy coding some demos to some guy coding some rad SNES demos. So in 1991, 3 events happened that changed the world forever. The first one, in August 23rd, the Super Nintendo was released in North America. Now that's awesome, because then Super Nintendos were here. The second one, my parents bought a Super Nintendo. This is also rad. If this hadn't happened, I wouldn't be here talking to you, so thank them for that. The third one, I was born, and this was chronological order. So the SNES is literally older than me. That was a good year. Throughout my childhood, I played so much SNES. And I mean, we had other consoles too, but this is the one we kept coming back to. Games like Super Mario World, games like Top Gear, games like Zelda. Of course, my personal favorite, Chrono Trigger, which is the greatest game of all time. And don't you ever say anything else to me. I will stop talking to you for life. Thank you. Clay Fighter, anyone? Yeah, that game was actually terrible. Anyway, yeah, so I kept coming back to the SNES. And of course, as a kid, you see these games, and you see these things are your life. This is what you do when you're a kid, is play games. See, I always wanted to make this kind of stuff. Of course, I was like 4, so I couldn't do it. Around 2000, it must have been 8 or 9, I started learning web design from some girl in my class's mom or something. I could make like blue web pages and stuff. It wasn't much, but I started learning how to program. After a few years of this, I started learning about emulators. This is when I discovered, like, wow, I can play SNES games on my computer. Then I played way more SNES, which was just amazing. That can never be a bad thing. But then I really wanted to make games for this thing, but of course it was way too hard. Fast forward to 2008 or so to 2011. By now I'd been making a few kind of demos. I had started a group called Youth Uprising, and I went to my first demo party, NVScene 2008. Woo! Right? Shortly after that, I started working on doing 4K intros. I just thought that was such a cool, I guess, genre of demos. There's a classification. I don't know what the word is. Anyway, it was so cool because you got to do a lot of, well, assembler hacking, because I liked that a lot more then. And I thought, well, man, if I'm doing this on PC, I should probably be able to do this on SNES. Yeah, so I kind of started looking at that, but it was still too hard. I did some C64 stuff, and that was actually a lot better because it's a very similar CPU, but it's just a kind of a simpler system. And yeah, there's a lot more resources to kind of learn about it. There's a lot more demos to get inspired by too, so you kind of know what you're working with a bit more. But it never really clicked for me, just because I don't think it had the nostalgia factor that SNES always did. So I kind of dropped that for a while. Eventually, I went back to SNES later in the year. I didn't make that much progress. I had some scrolling things and joypad input, and that was basically it. Hardly anything useful. But I did start to see how these sort of larger programs would be written for these old systems and this sort of organizational things. But I still lacked the organizational skills necessary to do anything big. So I also dropped that for a while. Now this is over like a 3-year period. So I eventually went back to C64. I made a couple test demos, nothing that was very good. I never released anything. And one of the things I started noticing was that one of the big problems with these old school systems was data processing. So you have these really bad CPUs, but you usually have pretty good graphics hardware that can at least do lots of tiles and stuff. And so what you find is when you're doing a lot of these old school demos, it's much less about sort of CPU optimizing for cycles and stuff, and it's much more about like data processing and data preparation. The problem with that is that you end up, you need like a specific kind of data for your specific task, and so you kind of have to work with these really terrible tools that you basically are either really buggy or written by yourself. In most cases, both. And they tended to add like a lot of extra steps to the build process. It would have been really cool if I could just pack these sort of converters within the source that used them. So I could be like, here's my assembler file, load this image, compile time, do some stuff to it, and then I can just read that data. It turns out there was a tool that did this. It was called Kick Assembler.
and it was invented by, I don't remember, but there's another one called Dreams Assembler as well, but it's basically the same thing. And what it actually does is it sort of mixes, I don't know if you guys can read that, I apologize for the small font, but it sort of mixes like assembly with higher level macros, and in addition like vector math and things like that, these really cool libraries that allowed you to do much higher level things at compile time, which is exactly what I wanted. So I was really, really stoked about that. But still, I kind of lacked the organization skills to do anything big. So I dropped that kind of stuff again. I ended up going back to and trying Atari VCS coding, which is just sort of another nuts system. The thing about VCS, it has the same CPU as the C64. So I could still use Kick Assembler, and that was super helpful. I actually made it a bit farther on this system than I did with a lot of the other ones. I ended up making a custom sound driver and stuff. But the music is just terrible on that system, no matter what you do. Because it's a little 2-channel oscillator, kind of weird, stupid thing. And the pitches on the oscillators, you get a 30 kilohertz oscillator, and then you get divisors to set the pitch, which is, God, so bad. Anyway, not even the different waveforms on that chip are in tune. So yeah, left that again. But I did get a bit farther. Now, if we fast forward to November 2011, I was asked by the @Party organizers to do an invite for @Party 2012. And of course, I said yes. Those guys are fantastic people. I like that party. So I started work on a demo. Didn't really get that far, but I had like 6 months, so it didn't matter. But then when I went home for Christmas that year, and I started making Game Boy music just for fun, to have something to do on the plane, which is awesome for that, by the way. And of course, when I got home, then I was like, man, I got to try coding on this. So I started doing that. Again, I didn't really get anything fancy, just some scrolling things and, this and that. Unfortunately, about a week later, I was at a party and my laptop got stolen, which meant I had to buy just some kind of replacement netbook to have some kind of computer. It meant that I couldn't finish the PC demo, but I talked to the guys and I was like, hey, I'll do a Game Boy demo for your invite. Never done one of those, so let's try that. And of course, they liked it, so we started doing that. Now, the workflow for that demo is kind of strange, but this is where things started clicking for me with old school development. So I started with doing a couple of simple effects. I did smiley faces moving around the screen. I did some twisting effects. But the workflow is basically the same that I had with C64. It's a different CPU than C64, so I couldn't use that Kick Assembler tool. But I still did anyway to generate a lot of data sets and just output binary files, which actually worked pretty well. What I found is that this little scripting language that was in Kick Assembler is really, really, really slow. And it ended up being unusable for the kind of data sets that I had. Now, at this time, I was already working at a company called Outtrex. Now we're called Fuse. I still work there. And we were basically developing a programming language that abstracted shaders and allowed you to write CPU and GPU code sort of simultaneously. And so I was really interested in compilers at that time. And I thought, man, why don't I just make my own assembler with my own meta language and just make it way faster? Shouldn't be too hard, right? So, of course, I started that. And so the first kind of step to do that is to just do like a normal assembler without sort of meta-programming facilities. So I got that working fairly quickly in C#. Just 1 second. I'm going to pull up some stuff. Forgot about this. But yeah, what I realized is that after I built that, got everything up and running, that I really didn't have time to do the meta language part of it before and do the demo before the deadline, which is in like 4 months at this point. So what I did do is I started saying, well, like, okay, C# has these strings that can span multiple lines. So why don't I just like use those to write my assembler code and then just use C# in between those? So then it's kind of like hosting C# inside this assembler. And I can pull up some of what that looks like, because this actually worked out really well. Over here. So here you can see in this verbatim string here, I just got some assembler. Eventually I dump some constants in there. Here I do some pre-calc with my data sets. Here I unroll some loops. So this is actually a really nice way to work, because you have actual meta programming facilities. So all that data set generation stuff is pretty much taken care of. And this is my first taste of really doing this effectively. Of course, so that was enough. So I ended up finishing the demo. The demo was called Demon Blood. It was released at Pixel Jam 2012. It got second place. I believe the guys that beat me are here, which is pretty cool. Generally, what I realized is that this sort of hosting assembler and strings and using meta languages was a really, really good way to work, because then I didn't have to write the languages, but I could also get all the benefits. So then, after I finished that, I kind of took a break for a little while. We're going to fast forward to the summer of 2013. I really wanted to, when I wrote this assembler, just because I like to try lots of architecture things, I wanted to say, okay, this assembler works. Now I want to plug in different architectures. I want to use the same kind of technology for all the different CPUs that I want to code on. Of course, the code was a mess, so I started over. But then I started implementing the Game Boy stuff in parallel with the Super Nintendo stuff, because Super Nintendo is one of the harder architectures to write an assembler for, because it has weird switching modes and a lot of state and stuff. But it ended up starting to work out. By the time it was about September 2013, I had my first SNES ROM. It was just a green screen, but it worked, and that was really cool. I started to make a SNES demo because I was so pumped about this. I did some basic effects. I did like a sort of, if you've ever seen a Menger sponge, I did sort of a zoomer thing with that, with the infamous Mode 7 stuff that SNES is so famous for. I did a lot of kind of like just moving around logos and scrollers and just these sort of proof of concept things. And it was all really motivating, but it still took a lot of time. So I started wanting to come up with tools to handle, like, one of the things that you spend so much time writing code for is just moving things in and out of memory. And this is just like, well, for Effect 3, I just needed this logo to be at this part in memory. It's like there had to be a better way to do that. There had to be a way to, like, I mean, when you do normal demos, you have a nice sync tool, and like you've basically solved that same problem. I should definitely be able to solve the same problem for old school stuff. But of course, before I went into this too far, I realized there was also another unknown, which was that there pretty much are not music tools available for Super Nintendo. Basically, like at some point there were, because people were making music on this when they were doing the games. But you just cannot find them. The official tools sort of never leaked. Eventually, I did find something called XM SNES. And if you're familiar with tracker formats, you'll know what the XM part is. It's basically a format that just says, OK, here's a bunch of samples, and here's when they all play notes. And so there's a converter that can take these XM files and give you a binary blob that you can play on your SNES. Of course, this actually has some problems, because the SNES doesn't just play samples. It also has a little echo unit, has a filter, has a noise generator, and it has built-in sample compression. And none of this tool allowed me to play with any of that. So that was terrible. So I just felt icky using it. So I went the way that I always do, and I just said, well, I'll just make my own tool. That shouldn't be too hard. And so all October and November, that's what I worked on. And yeah, basically I started with making a Super Nintendo audio unit emulator, which actually isn't too terrible to do. It's just a little CPU that's, kind of like a little 8088, a nice little DSP. It's actually pretty straightforward, especially because there's a lot of references for other people who have done it. So then once you have that, then you write a music driver that will actually play the music on that system. And then you write a front end, which is a tracker. And I can actually show you guys that. Really cool. We're going to be open sourcing this. I got, if you ever heard of Citrix, he's a chiptune artist out of Australia. So he's sort of helping me design some of the user experience kind of components. We still consider this a pretty early project, but it's rad. It's pulling up Visual Studio and building. There we go. So this, that looks like it works. I can play the stuff. And there, my audio is muted for some reason. I got this. There we go. So this is just sort of your standard tracker. I mean, it has, you can see notes playing and stuff. Over here, different samples. Things are a bit chunky because of Retina issues on Windows that I haven't fixed yet. this thing works. And of course, we have the all-important one-click ROM export, which is really, really cool. You'll hear that song later. Yeah, so that actually ended up working really well. Like I said, we're going to also be opening sourcing that tool hopefully by the end of the year. Really excited about that. But yeah, so now I had a what you hear is what you get tool, and that's just the coolest thing. So this whole thing is where I just got so stoked about what I was doing. Just be rad, be rad. It was so cool. So this is when I decided I would commit to a demo. This must have been October. So I had about 6 months until revision the next year, or whatever party I ended up at. I said, I'm going to make a demo. And so I sort of continued on just sort of making effects. You know, I mean, this demo had to be like really, really cool. It had to, it had to have the coolest visuals. It had to be the best SNES thing ever. The problem is that we also sort of entered crunch time at work, and so I had to put this on hold for a few months. By the time I was able to pick it up again, I had to do a demo in 3 weeks on a system that I had never finished a demo for in my life. So this is scary. But here's the thing. It had to run on SNES. Cool, I have tools for that. It had to have awesome music. Great, I got a tool for that too. It had to have awesome sync and look really good. That's not really something I had an answer for yet. At this point, I really just had a few lame test effects and no real way to sort of put the effects together. I learned when I did the Demon Blood demo that when I strung together effects, I'd basically just call a subroutine that would run the effect, and then it would count how many frames it ran, and after X frames it would return or something. This is a terrible way to make a demo. Even if you want to do synced screen flashes, imagine how many cycle counts you do. And then imagine if you move effects, and then everything's wonky and terrible. This is not the way we should be doing this kind of thing. But the thing was that I realized that if I'm going to do this demo in 3 weeks, I have to come up with something clever. The only way that I could come up to do this, some of you guys are going to hate me for this, some of you guys are going to think it's awesome. Video. I'm going to compress video for my visuals, and it's going to be rad. So with video, I could use sort of a normal demo workflow to generate visuals. I didn't have to be really that constrained by the actual SNES constraints, because I could just make whatever. I could use my proper tools. I could do really good sync. I could do really good music. I could make this really proper. Then the only SNES code I would have to write, which is going to be the time-consuming part, is sort of the replayer for this video. Of course, this would also mean the video had to be simple enough to be able to be replayed on the SNES. The DMA unit I mentioned earlier is basically your modus operandi for this. And the thing is, it has actually pretty good throughput, but we'll see later that doesn't always mean that that's very consistent, and it's tough. But I mean, more than half of a demo for an old school platform seems to just be moving data into the right kind of memory before you display it. And even if you're doing CPU effects, there's so much bookkeeping between them. And I just sort of realized, maybe if I try this video thing, maybe I'll come up with some knowledge that will help me in sort of a more real demo as well. So I went for it. I'd also never done video compression before. That sounded fun. So what is a video? Let's ask that question. A video is sort of a regular sequence of images. And by regular, I mean the images sort of happen one after another at regular intervals. Now, if you want to sort of represent images at regular intervals, the sort of obvious way that you would do that is you just imagine, oh, well, I have just these 5 images in a row, for instance. OK, great, 5 raw images. So I started with that. I started with that on the SNES, and I made that work. Turns out the DMA, if you're just doing 1 burst per frame, can do about 3 kilobytes of data to the video memory. That's enough. Makes sense if you're using a 4-color mode. That will totally work. Anyway, so I got this to work, and I did this little test that was about, I don't know, maybe 5 seconds of these little triangles spinning around. And that was 3 megabytes. So clearly that was not going to work. So let's talk about delta encoding. Now, most of you have probably heard what this is. This is pretty simple. If we take the sequence of numbers, 0, 1, 2, 3, 4, 5, 6, 7. This number has 8 unique symbols. Sorry. So this, in its current representation, takes 8 symbols to represent. But see, there's something about this that we can notice. We can look at this. We can model this and say, well, between each of those numbers, there's a value of 1. So if we take 0 and we add 1, we get 1. If we take 1, we add 1, we get 2. And that pattern is consistent. So we can encode the deltas instead. We can encode the first number, which was 0, and then we just encode all the deltas. We realized, hey, those are all the same number. If I know the length of my string, and I know that the first one is 0 and the rest is just going to be a delta, I can encode this in 2 symbols. So it's the same concept with video, except instead of numbers, you have images. So you take sort of 2 images, and instead of like displaying this and then displaying this, you say, well, what changed between these 2 images? And then all you have to do is store what changed and be able to update that. This is called temporal delta encoding. It's really fancy. I found someone else's slide that could explain this way better than me. Don't worry, I did quote them in the source there. Anyway, this is what it's showing. So you have the different images, and you have the actual difference. When you can encode that, then things actually start to make a lot of sense. So the rest is, okay, well, I can get that to work, but how do I represent this on the SNES? How is this format going to look? That's necessary for me to figure out. One of the things I always try is a virtual machine. They're fun to make. So I realized that I could do these 2 opcodes. One of them could load palette data. Given an address, a length, and a chunk of data, it can just stuff this data into palette memory and do the same thing with the VRAM. And it turns out this was actually enough. With these 2 opcodes, I could do this entire demo. All I had to do was generate a sequence of these that made sense. Well, that's actually not entirely true. There was 2 more that I need to do. One of them is that like when you hit the end of a frame, you need to stop moving data into memory. So what I can do is I can figure out all the differences of all my pictures and then encode them as, okay, what actually needed to change in video memory? What needed to change in color memory? Make those changes and then do an end of frame opcode. And so then what I could do is I had this little loop that could sit there and like call into my data stream. Like go here, it'll move some stuff into memory and then return. And then my data pointer's here. And I could do that over and over again. And that's how this whole thing works. This is just an example of what one frame might look like. Now it turns out this was actually good enough. I basically spent, 2 weeks tweaking this to make it actually work and be fast enough, and also to get good content. Of course, I also had to figure out what I was actually going to show in this video. So of course I went to beeplecrap.com. Beeple is a brilliant motion designer. Definitely recommend that. Anyway, what I came up with is this demo called New. Very, very inspired / ripped off of Beeple's 4-color process series. Very, very good. I'm going to play this demo for you now, and I'm going to talk about it a little more. Fire up the emulator. It's not this laggy on the system. I'll run the next one in a different emulator profile. Thank you very much. So so that pretty much worked, and we won the compo with that, and I'm still so thrilled about that. I did everything in that demo, except you could say I didn't do the design. Did all the music, all the code, everything, and it did work. If you can spot the artifacts too, I'll give you $100. They are there. So the next step was sort of refining this tech. Now I had this sort of video thing, and it kind of felt, cheap doing video. I mean, I am a demo scener at heart. I understand that. But I really thought that there was something to take from this. I really thought that there was, maybe doing pre-calc and figuring out which subroutine I'm calling every frame. Maybe that makes sense. I mean, that's not really cheap, because that's just figuring out logistics. That's pre-calculating logistics. Then I can figure out my actual effects later. And yeah, took a bit of a break. We'll fast forward again to August of 2014. This would have been about April last year. So then in about August, I just kept thinking about this virtual machine. I kept thinking, man, like, this is really cool, but what else can it do? What else can I do with this? And I started thinking, like, well, if I'm going to move away from sort of video, then I also, I want full control of the hardware. So, like, this tool already gave me enough to do video, but that's actually because it gives me enough to do video memory and color memory management. And so maybe if I could code against, something other than images, but actually code against data structures, that this could actually make sense. And then it sort of hit me with this. So like I have this per frame virtual machine. I can make it do whatever I want. I can change video modes. I can change hardware states in addition to moving memory. And here's the kicker. It only actually took one opcode. I could actually do a store byte opcode, and that's actually enough to generalize all the other things I wanted to do. So instead of just moving memory, I could also change the video mode. And as long as I had a nice way to, to figure out which frame I was going to do that, I had a system that would make this work. And that's pretty cool. So then all I really need to, actually technically the other two opcodes I can also implement now with this store byte opcode. But it's, faster not to, and it's not that important. But Steve, this still didn't go all the way for me, because then once I have this opcode and I know what I can technically do, this still doesn't give me the tool to do it well. So now I had all this cool tech. The problem was, yeah, like I said, reduced to the instructions. But it just didn't feel like doing video supplemented with some hardware register changes was very sexy. So yeah, I just kind of looked at like what did I really want? I wanted full control of the system. And so I thought, well, what would my ideal SNES coding environment look like? So I realized I could probably program in F#. I love F#, great functional language. If I use pure immutable data, that stuff makes me warm and fuzzy inside. And if I could compose, still build effects using code in F#, but then maybe sync with Ableton Live or something. Some really cool tool that gives me a nice sequencer that I don't have to do that myself. And then it hit me again that I actually totally could do this. Because with image compression, what you do is you have this data structure that represents an image. And you're just diffing those data structures. If I made a data structure that represented the state of the SNES hardware, I could do the same diffing process. And then I could start at some known state in the SNES hardware. And then every frame just update that SNES state a little bit based on these diffs that I could come up with in pre-calc. And I got this idea because I remember I was looking at Git. And I was looking at the history, and I thought, man, this is so cool. It has all this data, but it's still actually really small because it's just storing diffs. So you can go through that entire Git history and get to any point in that history just by applying diffs. And all that is just this little data structure that represents changes you would do on disk. And it's the exact same thing. I'm going to make a little data structure that represents changes that I'm going to do on the SNES hardware. So it's just more opcodes, really. And that is really cool. So yeah, as long as I made a data structure that represented the hardware registers, preferably sort of unrolled. Usually when you have a hardware register like a video mode or like a background enable register, you have different bits that represent which background is going to be enabled. I could expose these as booleans and then just encode them to bits when I do the diffing, that kind of stuff. It would also contain the video memory contents and the CGRAM contents, and then I could just code those however I want. I could, as long as I generated one of these structures for every frame that would run on the SNES, then I could do diffs from each one to the following one, and these diffs can be encoded as opcodes. And those were the things that would actually update the hardware state. It's a little bit confusing, but I will show you a little bit more about this. But it was just so cool because as long as I can, have this system that would work with diffing these states, I can generate these states any way I want, and that is awesome. So I did a lot of this tech over the next few months, and yeah, started the next demo. I'm going to cut the story time a bit short now because I really want to go over, this demo and sort of how I made it work. So let me actually try to switch video here so I can see what I'm doing. Sorry, video guys. Oh, that's a fun resolution. We'll get there. We're all in this together. Bloop. All right. Can you guys read that okay? Should I bump it up? We'll do this. How's that? A little bit better? This is the actual data structure that I have for my instructions, by the way. This is end of frame, end of bank, so I can hit the end of a bank and jump to the next one. End of transmission. Store bytes. I can also do HDMA channels, which is a really cool SNES hardware trick to change things per scan line. I can pre-calc all of that kind of stuff. Load palette data, video data, and sprite data. I support sprites now. I want to show you quickly this data structure that I'm talking about so you can kind of see what I'm thinking here. It's a fairly large structure because it encompasses the entire state of the hardware. Now, this is the SNES state structure. We have a screen-enabled bit, screen fade, integer, all that kind of stuff. All the different settings for background mode 1, all the different settings for background mode 2. Now, of course, it seems like it'd be really tedious to fill all these out. But the thing is that you can just take default values, and this language F# has syntax to just make a copy of it, but then only change a few things. And it turns out that I can abstract all those changes as well. I can say like blit this bitmap, and it'll give me a new state with that bitmap blitted into it and all that kind of stuff. So I can code this high level, in this higher level DSL almost against this data structure. And then they all just get diffed, and I just get this really cool code out. So, sorry? Zoom is off? Oh, yes. Thank you. Sweet. Yeah. So basically what this means is that I can, another advantage of having this state is I don't just have to diff them to figure out what I'm going to do on the SNES. I can also take this state as an input to a function that'll give me an image. And that's an emulator. So I can emulate what this state looks like, and then I can simulate it running on the SNES and work on things that way and tweak them that way. This takes a minute to load all the assets and do all my data pre-calc. And then, in my sort of sync tracker over here, I actually have the whole demo. This is how I work on the demo. And this is cool. So you can see here I have the, this is the actual video output. This is a visualization of the video memory. And then this is the visualization of the palette memory. Of course I have, lots of stuff that I can do. And the coolest thing is that then all I have to do is just run another project that just generates all those same frames in an order and does all the diffing. Stuffs it in a SNES ROM, and away I go. I won't let you sit. I won't make you sit through this whole thing because it is actually kind of a slow process. But you can see sort of the iteration time that I actually have to work with now is extremely fast because all those tracks you saw I can show you in a sec. I can drag those in real time and see what the actual effect on the SNES is going to be. And it feels so powerful. Yeah, so this is what it looks like when it's actually building the ROM. You can see it sort of fills up the video memory, then it shows the logo on screen, that kind of stuff. Does some flashing. That's a bit slow, so I'll save you the details there. And in fact, why don't we watch this demo real quick, so you see what I'm working with here. Do the performance profile this time. See if that helps. Emulator, where are you? I had a crew now by this point. I just want to let you know you're applauding F# code. 100%. Well, thank you. I'm quite proud of that myself. So let's, I can just finish it like this, I guess. We'll do this, makeshift slides. Yeah, so where am I now? Now I have this total pipeline for using F# to control SNES states. And this is a really good way to just do any kind of effects that I want, as long as those effects are clever utilization of the hardware that already exists. So the next step from this would be to also support the more classic CPU style effects, but I can still do that within this framework, because I can use this framework to say, okay, yeah, make sure everything in memory is in memory where I need it, and then I can call into user code every frame, and I can figure out which frames I'm going to do that, and I can figure out all the flashing and all that stuff as well. And all I need to do that is just implement one more opcode, which is just jump into user code somewhere. So I'm really close to having that as well. And then, of course, we're completely away from video, but we still took all the advantages of having this, being able to work, and what you see is what you get on this platform, basically through emulation and through these higher level languages and that kind of thing. So that's it for me. Thank you guys very much for coming. If you have any questions, I can entertain those now.